What if you were out in the water and needed to charge your battery for any reason at all? There are no outlets in the lake. What if an auto tracking solar system could charge your battery? Then guess what? I have the product just for you. The SS Imperium is an active solar tracker intended for marine applications. It is a closed loop system that can actively track the sun to generate the maximum amount of solar power throughout the day. This is accomplished using a two-axis system and a photoresistor sensor array that operates on shading similar to a sundial.
We designed from the perspective of this problem. How could we maximize energy captured from a solar panel on a moving vehicle? Our design needed to know where the strongest source of light was coming from and react to any changes in rotation of the body it was attached to. It would need to work autonomously, but would also need a remote user interface to allow for user control and data logging. And the design must work effectively as a closed loop, using the battery and solar panel before being connected to other systems.
The SS Imperium's chassis features handles, as well as safe grips on the lower body so it can be carried. Two hinge locks prevent the upper and lower bodies from rotating during transportation. These hinges are secured using trailer hitch pins for ease of installation and removal. The SS Imperium uses its light sensing fin to calculate direction, similar to a sundial, by creating shaded areas based on the sun's location. Rotational and positional instructions can be calculated from reading the values of the photoresistors and reducing the area of these shaded regions on the fin. The SS Imperium utilizes one linear actuator and one DC motor to move itself. The linear actuator adjusts the solar panel in the theta axis in the spherical coordinate system, similar to pitch on a boat, and the DC motor adjusts the panel in the phi axis, similar to yaw on a boat. For the angle of the solar panel to the sun, or rotation at about the theta axis, our design should start at 0 degrees, or parallel to the sun's horizon, and move up to an angle of 50 degrees. For the rotation of the solar panel, or rotation around the phi axis, the project should have full 360 degrees of rotation. The SS Imperium also features external solar panel wattage and battery voltage monitors, a companion Android application, and key ignition. This provides the user with useful feedback on the performance of the unit at any given time. The key ignition disconnects the battery for long-term storage. The solar charge controller controls all the 12-volt battery management and charging by using the solar panel's output. The charge controller also provides many protections, such as short circuit, overcharge, over-discharge, and reverse protections. The battery used on the SS Imperium is a sealed lead-acid battery, which provides more protection from lead-acid battery fumes than a standard flooded lead-acid cell. The battery can easily be scaled up to a larger size based on the user's needs.
The SSI runs on a multi-threaded Python script to handle user communication simultaneously to controlling multiple motors and logging data. The program can be divided into 4 simple components. First, the main process, which starts the subprocesses for the Bluetooth server, linear actuator controller, and DC motor controller, seen referenced as Blue, LA, and DC, respectively. The blue thread initializes the Bluetooth server and waits for any reception from the companion app, which will be discussed in further detail in the next section. The 2 modes, user and auto, can be selected in the companion app. The Bluetooth thread will handle switching between modes as other threads change behavior depending on the selected mode. When in user mode, the Bluetooth server waits to receive packets from the companion app. The server will either respond with a data packet for the live update feature of the app, or it will disperse the movement instruction to the motor control threads through an instruction queue. The linear actuator and DC motor control threads operate similarly to one another. They wait for the main or Bluetooth threads to push to their respective instruction queues, and on receiving an instruction, operate their motor as such. Either motor controller takes the commands stop, forward, or backwards, relative to the motor's function on the device. After starting these threads, the main program enters its control loop. When in auto mode, it will send instructions to each of the motor controllers after running the data from the photoresistors through a decision matrix. The decision matrix seeks to have each sensor have as high a light value as possible relative to each sensor's history, while also keeping the sensors balanced through comparing their normalized values. This is how a fast, light-attracted, staring at the sun system is created. The companion application is a simple Android app that sends instructions to the Raspberry Pi. Already being paired with my Android, when I press connect, it will quickly create a Bluetooth connection. Once the connection status reads as good, we can start reading updated values from the device. Right now, the app is able to give live values for the positions of the linear actuator and DC motor in degrees, and the charge value of the onboard battery. although these values may sometimes be inaccurate due to noise in the electrical signals and whether power is being drawn from the battery. At the bottom of the screen is a window that displays logged messages from the app, including connection logs and instructions being sent and received. While initially in auto mode, I have started this session in user mode by switching before the connection is made. As soon as the connection is good and the control buttons are activated, we can begin controlling the device. First, raising the panel. Lowering the panel. I like this position, so I'll go ahead and hit stop. And rotating right. Next, we'll try rotating left. Let's stop here again. The app can control the state of the device, either being in auto or user mode. We can relinquish control to the computer by tapping the user enable switch once more, which will return us to auto mode. In this lab setting, our device is given our construction light sun to track. We first flash the photoresistors with our sun to give the device a max value to use in normalizing the sensors. This is only important in a lab setting. You will see the device working in outdoor conditions shortly after this lab demo. Once the device is running in auto mode, it will use the 4 photoresistors to determine the direction of the brightest light source. Difficult as it may be in this lab with plenty of ambient overhead lights to compete with our sun, the device is able to react quickly and track correctly, given a little persuasion.
The SS Imperium's intended use is for it to be placed outside, on a vehicle, set to its auto mode, and let free to track the sun as the vehicle moves, keeping in line with the angle of the sun through the day or reacting to a change in vehicle position and rotation. Once the device has found an optimal angle, it will not continue moving unless a threshold for movement is reached. As shown on the watt meter, we had a 5 times greater power efficiency than at level for the solar panel. This is a massive improvement over a standard fixed angle solar panel system.
Strengths of our system. The multi-axis tracker can find the most efficient position for generating maximum power. It is very easy to swap out the battery and easy to use the app for manual operation. There are many monitoring systems to give the user useful feedback on the unit's performance.
With our latest design, there are a couple of weaknesses we have with a prototype that could be fixed in a final design. For example, it doesn't respond exactly automatically. It does take time to find the right position. It's also not waterproof. I would recommend to not bring it on the water yet unless you want to make a very, very damaging mistake. And, for example, aluminum design would be more durable to the elements and make the entire project more lightweight for the system. With all of these taken into account, for a final prototype, this would be perfect to take out into the water for your boating needs.
We'd like to reiterate our thanks to the Clemson University Holcomb Department of Electrical and Computer Engineering for helping to fund critical equipment to our design. And thank you for watching.